Hello there, and welcome to the Sleepy Space Channel. Tonight, the strange and quietly unresolved gap between the number of worlds in the galaxy that could plausibly support life and the number of worlds we know to actually host it. The first number is enormous. The current best estimates place tens of billions of habitable zone planets in the Milky Way alone, with quintillions across the observable universe. The second number, the count of worlds where life has been directly confirmed, stands at exactly 1, and that 1 is our own. Tonight we walk slowly through the catalogue of plausible homes between those two figures. Kepler 22b. Kepler 452b. Proxima Centauri b. The 7 Earth-sized worlds of TRAPPIST-1. The hycean candidate K2-18b, with its faint atmospheric chemistry. And the deeper, quieter question of which of these worlds, if any, may already be inhabited tonight without our knowing it. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The question and the long catalogue. The galaxy has been keeping a quiet catalogue for as long as there have been stars to keep it. Most of that catalogue has never been seen. A small portion of it is beginning, slowly, to be added up. The story of how many worlds in that catalogue might be capable of holding life is the story we are sitting with tonight. It begins with a number that has been changing every month for the better part of 20 years. The confirmed exoplanet count, the number of planets around stars other than the Sun that astronomers have positively identified, has now passed roughly 6,000. The candidate count, the number of probable detections that have not yet been formally confirmed, is several times higher than that. Inside that catalogue, in the slow drift of all those discovered worlds, a much smaller subset has emerged. A subset of planets that sit in the temperate ring around their host stars where liquid water could in principle exist on the surface. A subset, smaller still, that are small enough and dense enough to be considered rocky. And from those structured numbers, the field has begun the unsettling and patient work of trying to answer the question that lives behind all of them, which is the question of how many other worlds, anywhere, in any direction we can look, might right now be capable of supporting life. The question, properly framed, lives at 2 layers. There is the question of the named candidates. The specific worlds, by name, by host star, by orbital distance, that have already been catalogued and characterized in enough detail that we can speak about them as places rather than as statistics. That layer is the easier of the 2. There are a few dozen good answers to it. Each of them comes with a small fact sheet of mass and radius and orbital period and host star type. Each of them, even at the edge of what we currently know, can be held in the mind as something more than a number. There is the planet Kepler 22b, 700 light-years away, the first habitable zone world ever confirmed, around a star very similar to our Sun. There is the planet Proxima b, 4.24 light-years away, orbiting the very nearest star to us. There is the entire small ordered system around the dim ultra-cool dwarf called TRAPPIST-1, with 7 Earth-sized rocky planets stacked in resonance, 3 of them sitting in the habitable zone, all of them less than 40 light-years away. There is the larger sub-Neptune K2-18b, with its hydrogen atmosphere and its possible underlying ocean, and the chemical signatures that are being quietly read out of its skies by the James Webb Space Telescope. There is the smaller and more recent Kepler 1649c, almost the size of Earth, almost the temperature of Earth, 300 light-years away, around a small, cool star. Each of these worlds has a name. Each has a story. Each has a small, softly held place in the catalogue. Then there is the second layer, which is the population question. How many such worlds exist across the Milky Way as a whole? How many across the wider universe? That layer is much harder, because it requires extrapolating from the small biased sample of detections that current instruments have produced to the much larger population that we cannot yet see. The current best estimates of how many Earth-sized planets sit in the habitable zones of Sun-like stars cluster between roughly 30% and roughly 80% of all such stars. Applied to the 400 billion stars of the Milky Way, that yields an estimate somewhere in the tens of billions for the number of plausibly habitable worlds in our galaxy alone. Applied to the observable universe, with its hundreds of billions of galaxies, the estimate climbs into numbers that are no longer numbers in any felt sense. The answer to the question of how many habitable planets are really out there is, by the simplest reading of the available evidence, very large. The galaxy is very likely full of them. The universe is almost certainly full of them. That is the headline answer. It is also only the beginning. A note before the catalogue itself. The question of whether a planet is habitable is not the same as the question of whether it is inhabited. The first asks whether a planet has the architectural conditions under which life as we know it could plausibly survive. The second asks whether life is actually there. The first can be partially answered by observation. The second requires either the direct detection of a biosignature in the planet's atmosphere or, eventually, a probe. The two questions are often quietly conflated in popular coverage. Tonight, we will hold them gently apart. A habitable world is a world where life could exist. An inhabited world is one where it does. We currently know of exactly one inhabited world. We can speak with much more confidence about the candidates for habitability. The toolkit by which the catalogue is built is worth a brief, calm walk before we begin. 4 detection methods are doing most of the work. The first is the transit method, in which a planet passing in front of its host star, viewed edge-on from Earth, produces a small periodic dip in the star's brightness. A Jupiter-sized world, transiting a Sun-sized star, produces a dip of about 1%. An Earth-sized world, transiting a Sun-sized star, produces a dip of about 1/100%. The dip happens only if the orbit is oriented edge-on to us, which is only true for a small fraction of all planetary systems. But for those that are oriented correctly, the method yields the orbital period and the planetary radius with high precision. The Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, are the principal transit instruments. Together they have produced most of the confirmed catalogue. The second method is radial velocity, also called the wobble method. A planet's gravity pulls its host star into a small mutual orbit around the system's barycenter, the center of mass of the system. The star's motion toward and away from Earth produces a small periodic Doppler shift in its spectrum, the wavelengths of its light shifting slightly blueward when it moves toward us and slightly redward when it moves away. Jupiter pulls the Sun at about 13 meters per second. Earth pulls the Sun at about 9 centimeters per second. Modern spectrographs are approaching the precision needed to measure shifts that small. The method yields mass with a small ambiguity due to unknown orbital inclination and orbital period. The third method is direct imaging. Physically separating the planet's light either reflected starlight or its own thermal glow, from the overwhelming glare of the host star. Currently feasible only for very young, very hot, very widely separated worlds. Will become possible for Earth analog worlds only with the next generation of large, space-based observatories. Yields atmospheric spectra and surface conditions in principle. The fourth method is gravitational microlensing. A chance alignment in which a foreground star passes in front of a background star, momentarily lensing and amplifying the background star's light, and a planet around the foreground star leaves a characteristic signature in that amplification curve. The method detects planets that the other methods miss. Cold orbits far from the host star. Free floating planets with no host star at all. But it offers little follow-up. Once the chance alignment passes, the system cannot be re-observed. Together, these four methods have produced a catalogue of several thousand confirmed worlds. Each method has its own detection bias. Transit favors close-in planets around small stars. Radial velocity favors massive planets close to bright sun-like stars. Direct imaging favors hot young worlds at wide separations. Microlensing favors cold and free-floating planets. The fact that the catalogue is heavily biased toward close-in transit detections is the central reason why the population-level estimates of habitable worlds depend so heavily on careful statistical correction. Astronomers are not counting habitable worlds. They are counting the detectable ones and then inferring the rest. A working definition of habitability, the one most often used in the field, is this. A world is habitable if, given an Earth-like atmosphere and reasonable surface pressure, liquid water could persist on its surface for geologically long timescales. The definition is doing three quiet jobs at once. It is using liquid water as a proxy for the conditions life on Earth requires. It is requiring surface presence, not deep subsurface presence. And it is requiring geological persistence, not a transient warm moment. This is the conservative definition. It is the one most often used in the popular framing of the habitable zone. It is not the only definition in use. Later in the catalogue, we will return to several stretched and softer versions of habitability, each of which broadens the count in its own way. With the question shaped and the toolkit laid out, the catalogue itself can begin. Part 2. What the habitable zone really means. Before the catalogue itself, it helps to walk slowly through what the phrase habitable zone actually means. The phrase is older than the modern exoplanet era. It has been in use since the middle of the 20th century, when astronomers first began to formalize the question of where, around a given star, a planet could hold liquid water on its surface. In the years since, the definition has been sharpened, broadened, narrowed, qualified, and softened. It now has at least 3 commonly used versions and a number of less commonly used ones. The script that follows the headline number deserves a clear sense of which version is being used and what each one actually rules in and rules out. The conservative habitable zone is the simplest of the 3. It is the orbital range around a star within which a rocky planet, given an Earth-like atmosphere and reasonable surface pressure, could maintain liquid water on its surface at temperatures between 0 and 100 degrees Celsius. The inner edge of the conservative zone is set by what astronomers call the runaway greenhouse limit. As a planet moves closer to its star and absorbs more energy, water vapor increases in its atmosphere. Water vapor is itself a powerful greenhouse gas. The added water vapor traps more heat. The trapped heat evaporates more water. The cycle is positive and reinforcing. At a certain critical distance, the cycle becomes unstable. The oceans boil away into the atmosphere. The water vapor eventually escapes to space, broken apart by ultraviolet radiation. The planet ends with a dry, hot surface and a thick, lifeless atmosphere. The outer edge of the conservative zone is set by what astronomers call the maximum greenhouse limit. As a planet moves farther from its star, more and more carbon dioxide is needed to keep the surface warm. At some point, the carbon dioxide itself begins to condense out of the atmosphere as ice. Once it begins to condense, the greenhouse effect collapses. The planet freezes. For our own Sun, the conservative habitable zone runs from roughly 0.95 astronomical units, just inside Earth's orbit, to roughly 1.37 astronomical units, well past Mars. Earth at 1 astronomical unit sits comfortably inside this range, near the middle. Venus and Mars are the canonical end-member failures of the conservative zone. Venus, at 0.72 astronomical units, is well inside the inner edge. It is the runaway greenhouse outcome made real. Its surface is hot enough to melt lead, its atmosphere is 90 times denser than Earth's, and its water inventory long ago dissociated and escaped to space. Mars at 1.52 astronomical units is just outside the outer edge. It shows clear geological evidence of past surface water, suggesting it was once habitable before its atmosphere thinned and its surface froze. Of 3 rocky planets in the temperate ring of the solar system, 1 worked. 2 did not. The solar system has, in effect, run the experiment 3 times. The optimistic habitable zone is a wider boundary. It is defined less by theoretical limits and more by the empirical evidence of past liquid water on Venus and Mars. If Venus once hosted oceans for as much as 100 million years before its runaway greenhouse fully engaged, the inner edge of habitability may sit closer to the star than the strict runaway limit suggests. If Mars hosted lakes and rivers and shallow seas for hundreds of millions of years before its atmosphere thinned, the outer edge may sit farther out. The optimistic zone for the Sun runs roughly from 0.75 astronomical units to roughly 1.77 astronomical units, a band almost twice as wide as the conservative one. Most popular headlines about Earth-like worlds use the optimistic zone. Most peer-reviewed statistical estimates use the conservative one. The choice changes the inferred number of habitable worlds in the galaxy by a factor of roughly 2. For different host stars, the habitable zone sits at different orbital distances. A small, cool red dwarf has a habitable zone that hugs much closer to the star. For the smallest M dwarfs, the zone is at fractions of 1/10 of an astronomical unit, with orbital periods measured in days rather than years. A large hot F, or A-type star, has a habitable zone that sits farther out, with orbital periods measured in years rather than days. The shape of the zone scales with the host star's luminosity. The same temperature window can sit at radically different orbital distances depending on the star at its center. The phrase that needs to be held quietly before we go further is this: the habitable zone is a temperature window only. Being inside it is necessary for surface liquid water. It is very far from sufficient. A planet inside the habitable zone can still be uninhabitable for any number of independent reasons. It can have no atmosphere at all, or an atmosphere too thin to hold heat, or an atmosphere so thick that it greenhouses the surface to runaway temperatures. It can be tidally locked, with one hemisphere baked and the other frozen. It can be stripped to bare rock by stellar flares. It can lack a magnetic field, allowing the stellar wind to peel its atmosphere away over geological time. It can lack plate tectonics, leaving no carbon cycle to regulate its climate over billions of years. It can lack a stabilizing moon, allowing its rotational axis to wander and producing extreme climate swings over tens of millions of years. It can be the wrong size, too small to hold gases, or too large to remain rocky. It can be in the right place but the wrong system architecture, perturbed by neighboring planets onto a chaotic orbit. The habitable zone is, in the cleanest available metaphor, the address on the envelope. Whether life is actually inside the envelope depends on what is in the letter. Several of these architectural conditions are worth a small additional pause. Magnetic fields, for instance. Earth has a magnetic field generated by the slow churn of liquid iron in its outer core. The field deflects the solar wind, the stream of charged particles continually flowing outward from the sun, and prevents the wind from stripping away the upper atmosphere. Without that field, the solar wind would have eroded Earth's atmosphere over billions of years, much as it did on Mars. Mars once had a magnetic field, generated by its own once molten core. Sometime, around 4 billion years ago, the core cooled and the dynamo shut down. The magnetic field faded. The solar wind began to strip the Martian atmosphere. Over the next billion or so years, that atmosphere thinned, the greenhouse effect collapsed, and the surface water froze or escaped. Whether a planet has a long-lived magnetic field depends on whether its interior remains hot and molten enough to sustain a dynamo, which depends in turn on its size, its composition, and its tidal environment. Of the rocky worlds in our own habitable zone, only Earth currently has one. That is not a small detail. It is one of the central reasons we are here. Plate tectonics are another. On Earth, the slow movement of the surface crust over billions of years has acted as a thermostat. When the atmosphere warms, rain falls more heavily, weathering exposes more rock, and the weathering reactions pull carbon dioxide out of the air and lock it into ocean sediments. When the surface cools, the rain slows, the weathering slows, and volcanic outgassing releases carbon dioxide back into the air. The cycle balances itself over millions of years. It has kept Earth's temperature in the habitable range despite the slow brightening of the sun across billions of years of stellar evolution. Without plate tectonics, the carbon cycle does not close. The thermostat is missing. The climate cannot stay stable for long. Venus probably lacks plate tectonics. Mars almost certainly does. Earth has them, perhaps because of some combination of its size, its water content, and its history. Whether plate tectonics are common on Earth-sized rocky worlds elsewhere is an open question. A stabilizing moon is the third condition often listed. Earth's moon, unusually large for its planet, exerts a steady gravitational torque on Earth that has kept the Earth's axial tilt stable at about 23.5 degrees for billions of years. Without the moon, that tilt could wander between extreme values over tens of millions of years, producing climate swings far more violent than anything Earth has actually experienced. Most rocky planets in the galaxy probably do not have large moons. Earth has one because of an early collision with a Mars-sized body that flung enough material into orbit to coalesce into the moon. That collision was a low-probability event. The script can hold this gently. The moon is not a small detail either. A quiet host star is the fourth. Stars vary widely in their level of magnetic activity. Sun-like G-type stars are relatively quiet. K-type stars, slightly smaller and cooler, are quieter still. M-type red dwarfs, the most common stars in the galaxy by a wide margin, are often the opposite. Many of them produce frequent superflares, brief, brilliant outbursts of UV and X-ray radiation, hundreds or thousands of times more energetic than anything the Sun produces. A planet in the habitable zone of such a star, even one with the right temperature, may have its atmosphere stripped away repeatedly across its history. Some M-dwarfs are unusually quiet, with low flare rates and stable output, and these are the M-dwarf systems that current habitability research treats most seriously. Ross 128 is one such example. TRAPPIST-1 is comparatively quiet for its size. Teegarden's star is another. The fact that the host star is calm changes the habitability prospects of every planet around it. The galactic habitable zone is the last layer of the conditional ring. The Milky Way as a whole is not uniformly hospitable to long-lived planetary life. Closer to the galactic center, the stellar density is higher, the supernova rate is higher, and the radiation environment is harsher. Long-term surface biospheres in that region face frequent catastrophic resets. Farther from the galactic center, the metallicity of the gas, the fraction of heavier elements available to form planets, drops below the level needed to make Earth-mass rocky worlds in significant numbers. Combined, these two limits define a thin annular ring roughly 7 to 9 kiloparsecs from the galactic center. The Sun sits roughly in the middle of this band, at about 8 kiloparsecs. Within the ring, the metallicity is high enough for rocky planet formation. The supernova rate is low enough for biospheres to persist, and the stellar population is rich and stable. Some estimates place the fraction of stars in the galactic habitable zone at 20 to 30% of the Milky Way total. The script does not need to lecture on this. It simply softens the headline number by a further factor. All of which is to say that when the press release reports a new habitable zone world, what is being reported is the simplest part of the question. The temperature window is right. The other conditions, the architecture, the field, the tectonics, the moon, the host star, the galactic location, the persistence over billions of years, all of those remain open. A confirmed habitable zone world is a real and important detection. It is the first step. The second step, the question of whether the world actually hosts life, requires patient atmospheric characterization, careful biosignature interpretation, and almost certainly the next 2 decades of new instruments to begin to answer. With the conservative and optimistic zones laid down, and the long list of further conditions held quietly in mind, the catalogue itself can begin. The first stop, by the order of historical discovery, is the planet that opened the door. Part 3. The stretchier definitions of habitability. Before we arrive at the named worlds, one more pause. The conservative and optimistic habitable zones assume surface water. They assume the question of habitability is the question of whether liquid water can sit, exposed, on the rocky outer face of a planet, beneath an atmosphere that holds it in. That assumption is built on Earth. It is built on our own experience of where life exists on our own world. It is not the only way habitability can be defined. Over the past 2 decades, a series of softer, broader definitions has emerged. Each of them stretches the count. The first stretch is the case of subsurface oceans. In our own solar system, the largest reservoirs of liquid water are not on the surface of Earth. They are buried beneath the icy crusts of moons. Europa, the smallest of Jupiter's 4 large moons, has a global subsurface ocean kept liquid by tidal heating from Jupiter's gravitational pull. The ocean sits beneath an ice shell estimated at somewhere between 10 and 30 kilometers thick. Beneath the ice, the ocean is in contact with a rocky seafloor, where hydrothermal vents may produce the kind of chemical disequilibrium that powers life around Earth's mid-ocean ridges. Enceladus, one of Saturn's smaller moons, has a similar subsurface ocean also kept liquid by tidal heating, and its ocean is leaking into space through cryovolcanic plumes at the South Pole. The plumes have been sampled by spacecraft. They contain water, salts, simple organics, and molecular hydrogen. The latter, a known biological energy source on Earth. Ganymede and Callisto, two more of Jupiter's large moons, also appear to have subsurface oceans. Titan, Saturn's largest moon, has both surface hydrocarbon lakes and a deep subsurface water ocean. Triton, Pluto, and possibly several of the dwarf planets in the Kuiper Belt may have subsurface liquid water as well. The total volume of liquid water in our solar system sits not on Earth and not anywhere else in the habitable zone, but in the cold outer reaches, far past the conventional maximum greenhouse limit. The total liquid water beyond the snowline of the solar system exceeds the liquid water on Earth's surface by an estimated factor of more than 30. Extended to the galaxy, this changes the population picture significantly. A small, rocky moon in tidal contact with a giant planet at almost any orbital distance can host a long-lived subsurface ocean. A free-floating rogue planet, ejected from its host star system into interstellar space, can host a subsurface ocean kept liquid by its own internal heat alone. Some recent calculations suggest that the total habitable volume in the galaxy, measured by subsurface liquid water in icy moons and rogue worlds, exceeds the total habitable volume measured by surface liquid water on Earth-like planets by many orders of magnitude. The galaxy may not be a place of many warm Earths. It may be a place of countless cold worlds with hidden oceans, sealed beneath ice, dark and silent for billions of years. The second stretch is the case of the Hycean worlds. A hycean planet, a name coined by combining hydrogen and ocean, is a sub-Neptune-sized world with a thick hydrogen-rich atmosphere and a global liquid water ocean beneath it. The class is hypothesized, not yet confirmed. The idea is that a planet larger than Earth, but smaller than Neptune, somewhere between 1 and 3 Earth radii, with a hydrogen envelope and a deep ocean beneath, could be habitable across a much wider range of orbital distances than rocky world habitable zones would predict. The hydrogen envelope acts as an insulating greenhouse layer. The ocean beneath can remain liquid even when the equilibrium temperature of the upper atmosphere is well below freezing. If the class is real, it could roughly double the population of potentially habitable worlds in the galaxy. We will return to the hycean candidates in their own dedicated stop later in the catalogue. For now, it is enough to know that the definition of habitability is in the process of stretching outward. The third stretch is the case of tidally locked terminator habitability. Many worlds in the habitable zones of small red dwarf stars are tidally locked, with one hemisphere always facing the star and one hemisphere always facing away. The day side is potentially scorched. The night side is potentially frozen. Conventional reasoning once treated such worlds as uninhabitable. More recent climate modeling has softened that view. A tidally locked planet with even a modest atmosphere will transport heat from its day side to its night side by atmospheric circulation. The result is a ring of moderate temperature at the terminator, the permanent twilight band between the lit and dark hemispheres. In principle, life could be sustained in that ring, beneath a sky in which the sun never sets, dim and red, hanging on the horizon for billions of years. Cloud feedback at the substellar point may further help. Thick clouds directly beneath the star may reflect enough light to keep the dayside temperature from running away. The mechanism is not yet observationally confirmed, but it is one of the major reasons modern researchers do not entirely rule out the M-dwarf habitable zone. The fourth stretch is the case of subglacial habitability. A world entirely covered in ice may still host habitable conditions beneath the ice, at the rock-ice interface, where geothermal heat, hydrothermal vents, and chemical disequilibrium can in principle support microbial life. Earth itself has examples. Lake Vostok, beneath nearly 4 kilometers of ice in Antarctica, hosts a microbial community that has been sealed off from the surface for millions of years. The community lives on chemical energy alone, drawing on the slow leak of nutrients from the surrounding rock and the slow melting of the ice ceiling above. Extended to the galaxy, this means that even a planet entirely outside any temperature-defined habitable zone could host life, given the right interior heat and the right chemistry. The fifth stretch is the case of the rogue worlds. A planet need not orbit a star at all to be habitable in the subsurface sense. The Milky Way contains an estimated several 100 billion rogue planets, worlds that were either formed without a host star or were ejected from their original systems during the chaotic early periods of planet formation. Recent microlensing surveys suggest that rogue planets may outnumber stars by a factor of several. Most of them are likely small. Many of them are likely cold all the way through. But the larger ones, the rogue super-Earths and rogue Neptune-mass worlds, can in principle retain enough internal heat from primordial radioactive decay to keep subsurface oceans liquid for billions of years. A rogue planet with a thick hydrogen atmosphere, drifting through interstellar space with no star to warm it, could maintain a subsurface ocean almost indefinitely. The galaxy may contain more habitable rogue worlds than habitable star-attended worlds. The sixth stretch is the case of the exomoons. The solar system has more potentially habitable moons than potentially habitable planets. Europa, Enceladus, Titan, possibly Ganymede and Callisto. By analogy, the galaxy almost certainly contains a vast population of habitable exomoons, large moons in stable orbit around giant planets, themselves orbiting in the habitable zone of their host star. None has yet been confirmed. The detection of exomoons is at the very edge of current observational capability. But the population is almost certainly real, and almost certainly larger than the population of habitable planets. A first confirmed habitable exomoon would substantially shift the count. These 6 stretches, taken together, expand the question of habitability from a narrow temperature window around a host star to a much broader question of where, in the universe, conditions exist that could sustain liquid water in some form. Taken at their broadest, the answer is that habitable conditions exist nearly everywhere. The galaxy is not divided into a small habitable ring and a vast uninhabitable wasteland. It is more like a slow scattering of pockets, each one small, most of them dark, most of them hidden, most of them sealed beneath ice, or wrapped in hydrogen, or drifting through interstellar space alone. The galaxy is, by this softer reading, almost saturated with the conditions life requires. Whether any of those pockets actually host life is a different question. We will return to it. For the rest of the catalogue, we will hold mostly to the conservative definition, surface liquid water around a host star, and to the named candidates that the field has converged on. That is the version of the question with the clearest available answers. The softer versions remain in the background as a quiet reminder that the count we are about to walk through is the floor and not the ceiling. The galaxy has many ways to keep water liquid. We are only now beginning to count them. Part 4. Kepler 22b. The first confirmed habitable zone world. The catalogue begins, properly, with Kepler 22b. It was the first exoplanet ever confirmed in the habitable zone of a star very similar to our Sun. Its confirmation, announced in late 2011 from observations taken by the Kepler Space Telescope, was the moment the modern habitable exoplanet era publicly began. Until that announcement, the question of whether any other star in the galaxy hosted an Earth-temperature planet had been only a statistical inference. With the confirmation of Kepler 22b, the inference became an example. There was now one named place to point to. The star at the center of the system is called Kepler 22. It sits in the northern constellation of Cygnus, about 620 light-years away. It is a G-type star, the same broad class as our own Sun, with a surface temperature about 300 degrees cooler and a radius about 97% of the Sun's. Its luminosity is about 79% of the Sun's. It is, in every meaningful sense, a slightly smaller, slightly cooler, slightly older version of our own star. It is the kind of host the field had been hoping to find, and Kepler 22b is the planet it turned out to be carrying. The planet itself has an orbital period of 290 Earth days. It completes a full circuit of its host star in slightly less than an Earth year, on an orbit at about 0.85 astronomical units, slightly closer to its star than Earth is to the Sun. Because its star is slightly cooler and slightly dimmer than the Sun, that closer orbit places it inside the conservative habitable zone, near the inner edge. Its equilibrium temperature, without any atmospheric greenhouse effect, is about 260 Kelvin, which translates to about -12 degrees Celsius. With a thick enough atmosphere, the surface would warm into the range where liquid water could persist. With an atmosphere very similar to Earth's, the surface temperature would be moderate, perhaps around 15 degrees Celsius, almost identical to Earth's average. The Earth Similarity Index, a composite metric that measures how close an exoplanet is to Earth across mass, radius, and temperature, places Kepler 22b at about 0.84. It is high. It is not the highest in the catalogue, but it was the first in the catalogue, and it remains one of the most studied. The most important detail about Kepler 22b is also the most uncertain. The planet has a radius of about 2.4 Earth radii. It is significantly larger than Earth. At that size, the planet sits in a transitional range between rocky super-Earths and gaseous mini-Neptunes. Without a direct mass measurement, the planet's true composition cannot be determined from the radius alone. If it is rocky, it is a heavy world with much higher surface gravity than Earth and a thicker atmosphere. If it is volatile-rich, it is most likely an ocean planet, possibly covered in a deep global ocean from pole to pole. If it is hydrogen-rich, it is a mini-Neptune with no rocky surface at all and a thick gaseous envelope wrapping a small interior. The radius alone cannot tell us which of these three possibilities applies. The most popular conjecture among researchers who have studied the planet is that Kepler 22b is most likely an ocean world. The reasoning rests on several lines of inference. The planet's size sits at the lower end of the mini-Neptune transition, suggesting it is less likely to have a thick hydrogen envelope and more likely to be volatile-rich. The density required to make it purely rocky would be unusually high, higher than is typical for super-Earths in the catalogue. A water world with a thick atmosphere and a global ocean is, by elimination, the most plausible configuration. If that conjecture is correct, then Kepler 22b's surface, if it has one beneath the ocean, has never been seen and never will be. The ocean itself would be tens or perhaps hundreds of kilometers deep. Above the ocean would be a thick atmosphere, perhaps cloudy, perhaps clear, depending on the planet's specific composition. There would be no continents, no shorelines, no archipelagos, just water, stretching from horizon to horizon, indifferent to whether anything is swimming in it. In the months after the confirmation announcement, individual researchers in informal interviews placed the odds of life on Kepler 22b as effectively certain. Some quoted figures in casual remarks rather than in formal published estimates, as high as 95 to 99%. These were not the field's consensus. They were enthusiasm. They were the discovery being absorbed into the public imagination at the moment it was first announced. The 99% chance of life framing is a real thing that real scientists really said, and it expresses something real, which is that the discovery of a habitable zone planet around a sun-like star so soon after the search began was not the conservative prediction. The field had expected such planets to be rare. They turned out not to be. The enthusiasm followed. The proper framing now, 15 years later, is more cautious. We do not know whether Kepler 22b is rocky, oceanic, or gaseous. We do not know whether it has an atmosphere, and if so, what it is made of. We do not know whether it is in synchronous rotation with its star, or whether it has Earth-like day and night cycles. We do not know whether its host star is sufficiently quiet to have preserved an atmosphere over the planet's long history. The planet sits in the habitable zone. That is established. Almost everything else is open. The discovery of Kepler 22b was the proof of concept. It demonstrated that habitable zone worlds around sun-like stars exist, can be detected by current methods, and can be characterized in enough detail to make further study worthwhile. Everything that came after Kepler 452b, the TRAPPIST-1 system, the rocky M-dwarf candidates, the Hycean class, followed from the door that Kepler 22b opened. It was the first planet to make the question into a question about specific named places rather than about statistics. It remains, in the catalogue, the one that came first. The script can hold the planet quietly as a possibly oceanic world, slowly tracing a not-quite Earth orbit around a not-quite Sun, 620 light-years away. A place whose surface, if it has one, has never been seen and may never be. A planet covered, perhaps, in a single ocean from pole to pole, beneath an atmosphere we cannot describe. A world that may host the conditions for life. A world that may host life itself. A world about which nearly everything that matters remains uncertain. The catalogue begins with it. The catalogue's first entry is a question. Part 5, Kepler 452b and the older cousins. 4 years after Kepler 22b was confirmed, the same instrument produced a second announcement that drew the same kind of attention. In mid-2015, the planet now known as Kepler 452b was announced as the first near-Earth-sized planet found in the habitable zone of a star very similar to our Sun. The press coverage at the time called the planet Earth's older cousin. The phrase is carried, even though, like Kepler 22b, the planet itself is larger than Earth. The star at the center of the system, Kepler 452, is a G-type star with a surface temperature within 20 degrees of the Sun's. It is slightly larger, slightly brighter, and importantly, older. Its estimated age is about 6 billion years, around 1.5 billion years older than our own Sun. The planet, Kepler 452b, sits at an orbital distance of about 1.05 astronomical units, almost identical to Earth's distance from the Sun. Its orbital period is 385 Earth days, within 5% of an Earth year. Its radius is about 1.6 Earth radii, larger than Earth but small enough to be plausibly rocky. Its estimated mass is about 5 Earth masses, which would give it a surface gravity of about 2 times Earth's. Its equilibrium temperature, given an Earth-like albedo and atmosphere, would be roughly comparable to Earth's. It sits in the conservative habitable zone of a star very similar to the Sun. By the conservative criteria of the field, Kepler 452b is a habitable world. The most striking thing about Kepler 452b is its age. Its host star is more than 1 billion years older than our own. If the planet is rocky and has retained an atmosphere, it has had longer than Earth has had to develop biological complexity. 1 billion years is, by the only example we know, the difference between a planet of single-celled microbes and a planet of conscious organisms looking back at the sky. If life arose on Kepler 452b at any plausible early date, it has had more time to evolve than life on Earth has had. That is not a small fact. It is one of the reasons the announcement drew the attention it did. It is also true, however, that Kepler 452b is beginning to face a problem of its own. The planet sits on the inner edge of the conservative habitable zone. Its host star, like all main sequence stars, slowly brightens over its lifetime by roughly 10% per billion years. As the star has brightened, the inner edge of the habitable zone has moved outward. Kepler 452b, fixed in its orbit, may be transitioning out of the habitable zone from the inside. Some climate modeling work suggests that the planet may already be in the early stages of a runaway greenhouse, much as Venus is believed to have undergone in our own solar system. Whether the planet has crossed that threshold, or whether it remains habitable for some hundreds of millions of years longer, is not known. The transition, if it is happening, is too slow for any observation to capture directly. A second caveat for Kepler 452b. In 2018, a follow-up statistical analysis of the original detection suggested that the signal may have been a false positive caused by stellar noise. The transit dip in the host star's brightness, the basis of the original detection, may have been an artifact of stellar variability rather than a real planet. The planet's status is currently considered uncertain. The discovery announcement still stands. The mainstream catalogue still lists the planet as confirmed. But the confidence with which Kepler 452b can be claimed as a real world is weaker than was first stated. The script can mention this honestly. The candidacy of Kepler 452b as a habitable world is real, but not as solid as the original press release suggested. Even with the caveats, the planet remains an interesting place to think about. If it is real, and if it has retained an atmosphere through its longer history, and if it is not yet in runaway greenhouse, then it is one of the most Earth-similar habitable zone worlds yet found around a Sun-like star. It is the place where the question of whether older Earth-like worlds can persist as habitable across more than 5 billion years is asked most directly. Whether they can, and what kind of place they become, is the second-level question that Kepler 452b carries forward. Several other planets in the Kepler catalogue fit the broader pattern of older cousins to Earth. Kepler 186f, announced a year before, Kepler 452b, was the first Earth-sized planet, that is, a planet within 10% of Earth's radius, found in the habitable zone of any star. Its host is a small M-dwarf, Kepler 186, about 580 light-years away. The planet's radius is about 1.1 Earth radii. Its orbital period is 129 Earth days. Its equilibrium temperature, given an Earth-like albedo, is around 180 Kelvin, which is cold, about -93 degrees Celsius, without atmospheric warming. With a thick enough atmosphere, it could in principle warm into habitable conditions. Without one, it would be frozen. Kepler 186. F carries the standard M-dwarf caveats. It may be tidally locked. Its host star is flare-active. Its atmospheric status is unknown. But by the strict size criterion, it was the first Earth-sized habitable zone world in the catalogue. Kepler 1649c, confirmed in 2020 from a reanalysis of older Kepler data, is one of the most Earth-similar candidates by size and equilibrium temperature. Its radius is about 1.06 Earth radii. Its host is an M-dwarf, about 300 light-years away. Its orbital period is 19.5 Earth days, which is short, but not too short for a small, cool star. Its estimated stellar flux is about 75% of what Earth receives, comparable to a slightly cooler Earth. It sits inside its host star's habitable zone. Its Earth Similarity Index is among the highest in the catalogue. It carries the same M-dwarf caveats as Kepler 186f. The host star is small and prone to flares. The planet may be tidally locked. The atmosphere is unknown. But the planet itself, by the simplest comparison, is one of the closest analogues to Earth currently known. There is also a broader category, the so-called superhabitable candidates, that is worth a brief pause. A small but growing body of work in astrobiology has proposed that some classes of planet might be more hospitable to life than Earth itself. The reasoning rests on several quiet observations. Earth's surface, while clearly habitable, is not necessarily the optimal configuration. A slightly larger world might retain more atmosphere, more water, and more interior heat for longer. A slightly cooler world might have less extreme climate gradients. A slightly older world might have more time for life to diversify. The superhabitable hypothesis lists several specific traits that, in combination, might produce a planet more habitable than Earth. A mass between 1 and 3 Earth masses, large enough to retain a thick atmosphere and abundant water indefinitely. A radius between 1.1 and 1.3 Earth radii. A surface temperature about 5 degrees warmer than Earth's average, extending the tropical band that on Earth hosts the highest biodiversity. A K-type host star, smaller and cooler than the Sun, with a main sequence lifetime of 20 to 70 billion years, compared with the Sun's 10 billion. An age of 5 to 8 billion years, older than Earth, but young enough that the star is still stable. A larger moon than Earth's, providing stronger axial stabilization and stronger tidal mixing in the oceans. Candidate superhabitable worlds named in the literature include several Kepler catalogue planets. KOI 571 5.01, a candidate with about 5.5 Earth masses around a slightly cool K-type star. KOI 555 4.01, another K-dwarf candidate at similar mass. Kepler 1126b. Kepler 69c. Kepler 1638b. None is confirmed as superhabitable. They are simply candidates that happen to score well on the proposed criteria. The superhabitable hypothesis is not the mainstream of habitability research. The mainstream still treats Earth as the calibration point and asks how close any given world is to Earth. The superhabitable framing flips this question and asks whether Earth itself is the optimum or merely one of a range of possible habitable configurations. The honest answer is that we do not yet know. We have one example of a habitable planet. We have no other examples to test the hypothesis against. The framing is a useful corrective. It reminds us that the planet we are on is the planet we are evaluating from, and that bias may be doing more work in the definition of habitability than we typically allow. Held together, the older cousins, Kepler 452b, Kepler 186f, Kepler 1649c, and the superhabitable candidates expand the catalogue of named places worth thinking about. Some are larger than Earth. Some are older. Some sit around stars that should last far longer than the Sun. None is confirmed inhabited. All are plausible homes. The catalogue is beginning to fill in. Part 6. Proxima b and the nearest stars. The catalogue, having taken in the Kepler discoveries at their various far distances, now turns inward toward the stars closest to the Sun. The nearest known potentially habitable exoplanet is also the nearest known exoplanet of any kind. It orbits the nearest star to the solar system. Its name is Proxima Centauri b, and it sits 4.24 light-years away at the doorstep of the Sun's stellar neighborhood. The host star, Proxima Centauri, is the smallest and dimmest of the three stars that make up the Alpha Centauri system. The two larger stars, Alpha Centauri A and Alpha Centauri B, are a closely orbiting binary pair of Sun-like stars, the closest such pair to the solar system. Proxima itself is a small M-type red dwarf with a mass about 1/8 of the Sun's and a luminosity about 1/7000th of the Sun's. It is so dim that, despite being the nearest star to us, it cannot be seen by the unaided eye. It is gravitationally bound to the Alpha Centauri A and B binary in a long, slow, hierarchical triple system, orbiting the inner pair at a distance of roughly 12,000 astronomical units and a period of roughly 550,000 years. Proxima Centauri b was confirmed in late 2016 by a careful radial velocity campaign that measured the host star's small periodic wobble. The wobble repeats every 11.2 Earth days, indicating a planet of at least 1.07 Earth masses, orbiting at about 0.049 astronomical units. That orbital distance is closer to the host star than Mercury is to the Sun by a factor of 8. But because Proxima Centauri is so dim, the planet receives roughly the same amount of stellar energy that Earth receives from the Sun. It sits, by the calculation of equilibrium temperature, near the middle of Proxima's habitable zone. Its equilibrium temperature, given no atmosphere, is around 234 Kelvin, about -40 degrees Celsius. With a thick atmosphere, it could warm into the range where surface water is possible. The minimum mass of Proxima b is 1.07 Earth masses. The true mass depends on the orbital inclination, which is not directly measured. If the orbit is close to edge-on relative to Earth, the true mass is close to the minimum. If the orbit is closer to face-on, the true mass could be significantly higher. The standard statistical correction, averaged over all possible inclinations, yields an expected true mass of around 1.3 to 1.4 Earth masses. By the simplest reading, Proxima b is a rocky planet of roughly Earth-like mass in the habitable zone of the nearest star to the Sun. Several things complicate that reading. The first is the planet's almost certain tidal lock. At 0.049 astronomical units from its host star, Proxima b experiences tidal forces strong enough that, over the 4 billion or more years of the system's age, its rotation has almost certainly become synchronized with its orbit. One hemisphere of the planet faces the star permanently. The other hemisphere faces away. The day side never cools. The night side never warms. Without an atmosphere to transport heat between the two, the day side would be hot enough to scorch most surface life, and the night side would be cold enough to freeze any volatile. With an atmosphere, the heat can be transported, and a moderate temperature terminator ring can form between the two hemispheres. Whether Proxima b has enough atmosphere for this kind of transport is the central open question. The second complication is the host star itself. Proxima Centauri, like most M dwarfs, is flare-active. It produces frequent superflares, brief, brilliant outbursts of ultraviolet and X-ray radiation. During the most intense flares, the flux at Proxima b's orbital distance can spike to 100 to 1,000 times the equivalent flux Earth receives during a strong solar event. Repeated over the 4 billion-year history of the system, this kind of stellar activity is capable of stripping away an unprotected atmosphere over geological time. Whether Proxima b has retained an atmosphere depends on its initial inventory of volatiles, on the strength of its magnetic field, and on the specific details of its orbital history. Some modeling work suggests the atmosphere has long since been stripped, leaving the planet as a bare rocky surface, lifeless, exposed to the full flare environment. Other modeling work, more optimistic, suggests that a strong enough initial atmosphere and a strong enough magnetic field could have preserved habitable conditions, particularly in the terminator twilight zone, despite the flares. The honest reading is that Proxima b is the floor of the optimism spectrum. It is the nearest known potentially habitable world. It may, in fact, be uninhabitable. It may host a thin remnant atmosphere, a permanent red dawn at the terminator, and conditions just inside the range that microbial life on Earth would tolerate. We do not yet know. The next generation of observatories, particularly the extremely large ground-based telescopes currently under construction, will be capable of directly imaging Proxima b and obtaining atmospheric spectra. Within the next 10 to 15 years, the question of whether Proxima b has an atmosphere at all should be settled. Whether it has a habitable surface beneath that atmosphere will take longer. Proxima Centauri is now known to host at least 2 other planet candidates. Proxima Centauri c, announced in 2020, is a candidate super-Earth at about 1.5 astronomical units from the host star. That orbital distance places it well outside the habitable zone, in the cold outer reaches of the system, far past the maximum greenhouse limit. Its mass is estimated at about 7 Earth masses. Its existence is now considered probable, but not yet fully confirmed. Proxima Centauri d, announced in 2022, is a small inner candidate, perhaps about 1/4 Earth mass, orbiting inside Proxima b's orbit at about 5 Earth days. Not habitable, but interesting for what it tells us about how packed M-dwarf systems can be. 3 planets within the orbital range that the solar system uses for Mercury alone. Beyond Proxima Centauri, the larger Alpha Centauri binary remains the closest pair of Sun-like stars to Earth. Alpha Centauri A is a G2V star, essentially identical to the Sun in temperature and only slightly larger in radius. Alpha Centauri B is a K1V star, slightly smaller and cooler. The pair orbit each other with a period of about 80 Earth years on a moderately eccentric orbit. Their closest approach is about 11 astronomical units, roughly Saturn's distance from the Sun. Their farthest separation is about 36 astronomical units, just beyond Neptune. The 2 stars are far enough apart, on average, to support stable planetary orbits in their respective habitable zones, although the orbital dynamics are more complex than around a single star. Whether the pair host planets in those habitable zones is one of the most active areas of current exoplanet research. Direct imaging programs are beginning to make tentative detections. In 2024, a candidate from a James Webb Space Telescope direct imaging program around Alpha Centauri A was reported. The candidate is preliminary, not yet confirmed, but its inferred orbital distance places it roughly in the habitable zone of Alpha Centauri A. If confirmed and characterized, it will be the nearest fully habitable Earth analog world known. The Habitable Worlds Observatory, currently in concept development for the 2040s, is specifically designed to image any Earth analog planet around the Alpha Centauri binary and obtain atmospheric spectra. If such a planet exists and the mission flies as planned, we will know within roughly 20 years. Several other nearby stars host candidate habitable zone worlds. The list is worth a small, calm walk. Wolf 1061c at 14 light-years, a super-Earth of about 4 Earth masses on the inner edge of its M-dwarf host's habitable zone. The host star is reasonably quiet for an M-dwarf, improving the planet's habitability prospects. Gliese 667cc at 23 light-years, a super-Earth of about 3.8 Earth masses firmly inside the habitable zone of its M-dwarf host. The host is part of a triple system, 3 stars in a long hierarchical orbit. Tau Ceti E and F at 12 light-years, candidate super-Earths in or near the habitable zone of a G8V star similar to the Sun. The detection of these planets is still debated. The radial velocity signals are present, but the interpretation is contested. Tau Ceti has long been a popular target for habitability speculation because of its sun-like nature and its closeness, but no confirmed habitable zone world has yet been found around it. Ross 128b at 11 light-years, a rocky planet of about 1.35 Earth masses, orbiting a quiet M-dwarf. Ross 128 is unusually quiet for an M-dwarf, with low flare activity, which substantially improves the planet's habitability prospects relative to most M-dwarf candidates. Teegarden star B and C at 12.5 light-years, 2 Earth mass candidates in the habitable zone of an old, quiet M-dwarf. Both have Earth similarity indices among the highest in the catalogue. Their atmospheric status is unknown. The catalogue of nearby candidates fills out the picture. Within a few dozen light-years of Earth, there are already several plausible candidates for surface or near-surface habitability. None has been confirmed as inhabited. All sit in the habitable zones of their respective host stars. Some sit around M-dwarfs, with the M-dwarf caveats. Some sit around G or K stars, with cleaner prospects but greater observational difficulty. The nearest fully confirmed Earth analog around a Sun-like star may still be waiting to be detected. It may be Proxima b, with a thin remnant atmosphere. It may be a Alpha Centauri planet, just at the edge of current imaging. It may be a Tau Ceti candidate that needs further follow-up. Whichever it turns out to be, the question of whether the Sun's immediate stellar neighborhood contains a habitable Earth-similar world is now within reach of the next generation of instruments. The catalogue's nearest entry is, by every available measure, getting closer to being filled in. Part 7. The TRAPPIST-1 system. The catalogue's next stop is the most famous multi-planet habitable candidate system known. It is also, by several measures, the strangest. The system sits 39.6 light-years from Earth, around an ultra-cool dwarf star, so dim and so small that it sits at the very boundary between true stars and brown dwarfs. The star is called TRAPPIST-1, named for the small telescope in Chile that first detected its planetary signatures. The system around it contains 7 confirmed Earth-sized rocky planets, 3 of which sit in the habitable zone. It is, by population alone, one of the most observed and most studied planetary systems beyond our own. The host star is an M8V ultra-cool dwarf with a mass of about 0.089 solar masses, almost exactly at the lower limit for hydrogen fusion. It is barely a star at all. Its radius is about 0.121 solar radii, slightly larger than Jupiter. Its surface temperature is about 2,500 Kelvin, the color of a dim red ember. Its luminosity is about 0.05% of the Sun's. Its estimated age is about 7.6 billion years, more than 3 billion years older than the Sun, which means it has been very slowly burning hydrogen at a very slow rate for a very long time. M-dwarfs of this size are expected to remain on the main sequence for hundreds of billions to trillions of years, far longer than the current age of the universe. TRAPPIST-1 will still be burning hydrogen long after every sun-like star in the galaxy has died. The 7 planets are remarkable not just for their number, but for their architecture. They orbit in a tightly packed, resonant chain. The orbital periods of consecutive planets form near-integer ratios. Planet B takes 1.5 Earth days to circle the star. Planet C takes 2.4 days. Planet D takes 4 days. Planet E takes 6.1 days. Planet F takes 9.2 days. Planet G takes 12.4 days. Planet H takes 19 days. These ratios are not random. Each planet's orbital period is mathematically related to its neighbors, in a chain of 3-body resonances that has held the system stable for billions of years. The configuration is similar to the Galilean moons of Jupiter in the solar system, where Io, Europa, and Ganymede are locked in a Laplace resonance. TRAPPIST-1 has the same architecture, scaled up to planetary distances. The full system fits comfortably inside an orbital radius smaller than Mercury's orbit around the Sun. From the surface of any one TRAPPIST planet, the others would appear as bright disks in the sky, sometimes large enough to show surface features. At closest approach between TRAPPIST, 1e, and F, an observer on either world would see the other as a disk roughly twice the apparent size of the Moon from Earth, with clear, visible features. The planets are, in a sense, each other's nearest neighbors, not in the abstract sense in which Mars and Earth are neighbors, but in the direct visual sense in which 2 ships at anchor in the same harbor can see each other's deck lights. The 7 planets, in order, are B, C, D, E, F, G, and H. Their radii range from about 0.77 Earth radii at the smallest, planet D and planet H, to about 1.13 Earth radii at the largest, planet G. None is significantly larger than Earth. None is significantly smaller. The bulk densities, as estimated from radius and mass, are broadly consistent with rocky compositions, with possibly some volatile component in the outer planets. By the simplest reading, TRAPPIST-1 contains 7 Earth-sized rocky planets in stable orbits around a single host star. The 3 habitable zone planets, E, F, and G, are the focus of habitability research. TRAPPIST-1, E, is the closest analog to Earth in the system. Its radius is about 0.92 Earth radii. Its mass is about 0.69 Earth masses. Its orbital period is 6.1 Earth days. Its estimated equilibrium temperature, given an Earth-like albedo, places it firmly in the habitable zone. Its Earth Similarity Index is about 0.95, the highest of any confirmed exoplanet in the catalogue. By every available measure, TRAPPIST-1e is the most Earth-similar world yet detected. TRAPPIST-1-4, with a radius of about 1.04 Earth radii and an orbital period of about 9.2 days, sits in the center of the habitable zone. TRAPPIST-1g, with a radius of about 1.13 Earth radii and an orbital period of about 12.4 days, sits near the outer edge. Both have somewhat lower Earth similarity indices than planet E, but both remain among the most Earth-similar worlds yet found. The system is, by population alone, the strongest available test of M-dwarf habitability. The James Webb Space Telescope has, since its first observations, made the TRAPPIST-1 planets one of its highest priority targets. The first results, from observations of the two innermost planets, have softened the initial optimism. TRAPPIST-1b and C, the two planets closest to the host star, show no detectable thick atmospheres. Their dayside brightness temperatures, as measured in thermal infrared, are consistent with bare rocky surfaces in direct equilibrium with the stellar flux. There is no thick atmospheric blanket transporting heat from dayside to nightside. There is no evidence of a substantial gaseous envelope. The two innermost planets are, by the most direct interpretation, naked rock, baked by their host star, like Mercury but smaller and dimmer. The implications for the habitable zone planets E, F, and G are not yet directly observed, but are not encouraging. If the innermost planets have lost their atmospheres entirely, then the outer planets, although less directly exposed to stellar wind and flares, may have suffered substantial atmospheric loss as well. The system's 7.5 billion-year history is long enough for significant atmospheric stripping even at the outer edges. Whether planets E, F, and G have retained any meaningful atmosphere at all is the question that the next round of JWST observations is designed to answer. The first direct atmospheric measurements of the habitable zone TRAPPIST planets are now being analyzed. The results will substantially refine the field's expectations for M-dwarf habitability over the next several years. For now, the system can be held quietly. TRAPPIST-1 is the strongest known multi-planet test case. Its three habitable zone candidates are the most Earth-similar worlds in the catalogue by size and temperature. Their habitability depends entirely on whether they have retained atmospheres against billions of years of flare exposure. The early observational signals from the inner planets suggest atmospheric retention may be weaker than was originally hoped. The outer habitable zone planets remain to be characterized. Whatever the next observations show, TRAPPIST-1 will remain one of the most important systems in the catalogue. It is the place where M-dwarf habitability is being tested at the population level. The answer it gives, optimistic or pessimistic, will shape how the field thinks about the habitable population for the next several decades. There is also the gentle fact that even if all three habitable zone TRAPPIST planets turn out to be stripped to bare rock, the system itself is a marvel. 7 Earth-sized rocky planets in stable resonance around a host star that will keep burning long after every other planetary system in the galaxy has gone cold. If life is anywhere in the system, in any form, in any subsurface environment, in any dim hydrothermal vent at the floor of a hidden ocean, it has, in some sense, the universe's longest possible time horizon. Whether or not the surface biospheres ever existed there, the system itself will be one of the last lights still burning when most others have gone out. That is its own kind of habitability question, and the script can let it sit in the background as the system passes. Part 8, K, 2-18b, and the Hycean candidates. The catalogue's next stop is a planet of a different category entirely. It is larger than Earth. It is not rocky in the conventional sense. It probably has a thick hydrogen atmosphere and a global liquid water ocean beneath it. It is the first and best-studied example of a new proposed class of habitable world, the Hycean planet, named for the combination of hydrogen and ocean. The planet is called K2-18b, and it sits 124 light-years from Earth, orbiting a small red dwarf at the inner edge of the constellation Leo. The host star, K2-18, is an M2, 5V red dwarf with a mass of about 0.45 solar masses and a luminosity of about 2% of the Sun's. It is moderately quiet for an M dwarf, but not as quiet as Ross 128 or Teegarden's star. K2-18b is the inner of two known planets in the system. The outer planet, K2-18c, is a non-transiting candidate detected only by radial velocity, and its orbital parameters are less precisely known. K2-18. B itself has a mass of about 8.6 Earth masses and a radius of about 2.6 Earth radii. By bulk density alone, the planet sits in the volatile rich category, too large to be purely rocky, too small to be a true mini-Neptune with a thick hydrogen envelope. The planet's orbital period is 33 Earth days. Its semi-major axis is about 0.143 astronomical units, well inside the inner edge of its host star's habitable zone by the simplest temperature calculation, but actually inside the habitable zone in practice because the host star is so cool. Its equilibrium temperature, given no atmosphere, is around 255 Kelvin, about -18 degrees Celsius. With a thick atmosphere, surface or ocean temperatures could climb significantly higher. The interesting thing about K2-18b is what the James Webb Space Telescope has begun to read out of its atmosphere. In 2023, an analysis of JWST observations reported the detection of methane and carbon dioxide in the planet's atmosphere, along with a notable absence of ammonia. The combination is consistent with the Hycean model. A thick hydrogen atmosphere over a global liquid water ocean with chemical or biological processes consuming ammonia and producing methane would produce exactly this signature. A pure mini-Neptune with a hydrogen envelope and no ocean would not. The atmospheric chemistry is the strongest available evidence that the planet may indeed be a hycean world. It is not conclusive evidence. It is a strong consistency check. The same analysis reported a tentative detection of dimethyl sulfide, a small organic molecule that on Earth is produced almost exclusively by marine microorganisms, particularly phytoplankton in the upper layers of the oceans. The detection of dimethyl sulfide in K2-18b's atmosphere, if confirmed, would be the most suggestive biosignature yet found on any exoplanet. The molecule is not produced in significant quantities by any known abiotic process. Its presence in the atmosphere of an ocean world would be difficult to explain without invoking some kind of marine biological activity. If the detection holds up to follow-up observations, it would be the closest thing to a confirmed biosignature the field has ever produced. The detection is, however, contested. The dimethyl sulfide signal in the JWST spectrum is faint and sits at low statistical confidence. Follow-up observations have produced mixed results. Some teams have reported strengthened evidence for the molecule's presence. Others have argued that the signal is more consistent with other atmospheric components, particularly with methane variations that mimic the spectral feature. The question is not yet settled. The proper framing now is that K2-18b shows the most suggestive biosignature observations to date, that the observations are consistent with the Hycean model and tentatively consistent with biological activity, and that confirmation requires additional follow-up over the next several years. The script should hold the K2-18b observations with deliberate calm. They are the most exciting biosignature observations of the era. They are also the kind of result that has been overinterpreted in popular coverage. The proper framing is that K2-18b is interesting, that it is consistent with the Hycean class, and that it is not yet confirmed as inhabited. The next several years of JWST observations and the next generation of ground-based extremely large telescopes will substantially refine the picture. By the late 2020s, the question of whether K2-18b is a Hycean world with biological activity should be much closer to settled. Several other planets have been proposed as candidate Hycean worlds. TOI 1452b, at about 100 light-years from Earth, is a super-Earth of about 1.7 Earth radii in the habitable zone of an M-dwarf host. Its bulk density suggests a substantial water component. Whether it has a hydrogen atmosphere is unknown but consistent with the available data. LHS 1140b, at 49 light-years, is another super-Earth in the habitable zone of an M-dwarf. Recent JWST observations of LHS 1140b have suggested that it may also be an ocean world with a hydrogen-rich atmosphere, although the atmospheric characterization is still preliminary. Kepler 138d, at 218 light-years, is an ocean world candidate based on density measurements. It is not strictly in the habitable zone, but is a useful comparison case. There are now perhaps a dozen named candidates for the Hycean class in the broader catalogue. None has been confirmed as habitable, but several show atmospheric chemistry consistent with the model. If the Hycean class is real, it has substantial implications for the population estimate. The conservative habitable zone, applied only to rocky surface water worlds, may be a substantial underestimate of where life can exist in the galaxy. Sub-Neptune-sized planets with hydrogen atmospheres extend the effective habitable zone significantly outward into orbital ranges that would otherwise be considered too cold for surface water. The class also has the advantage of being much easier to observe than rocky Earth analog planets. The thick hydrogen atmosphere is a strong spectroscopic feature, easy to characterize with current instruments. If Hycean worlds are common, they will be detected and characterized much faster than rocky Earth analogs. The first confirmed biosignature on any exoplanet may well come from a Hycean world rather than a rocky one. There is also a quieter category that the script can briefly hold: the hypothetical exotic candidates. Eyeball Earths, tidally locked worlds with permanent dayside oceans inside frozen nightside caps, producing the literal appearance of an eyeball from space when seen from the right angle. The dayside ocean, surrounded by a ring of ice. The nightside cap a frozen white circle. The terminator, a narrow band of permanent twilight. Frozen subsurface worlds with deep oceans, kept liquid by interior heat, analogous to Europa or Enceladus, but at planetary scale. Rogue planets with subsurface oceans, kept liquid entirely by primordial heat and radioactive decay, with no host star at all. Habitable moons of giant planets, the still hypothetical exomoons in their giant planets' habitable zones. None of these categories is confirmed as habitable. All are plausible. All are now being looked for. The catalogue is, in a sense, getting wider rather than longer. The number of distinct ways that life could exist on a world is increasing faster than the number of confirmed habitable worlds themselves. The script can close this part by sitting with K2-18b itself. 124 light-years from here, in the direction of Leo, a sub-Neptune-sized world is tracing a 33-day orbit around a small red star. Its atmosphere contains methane and carbon dioxide, and possibly, the small organic signature of microorganisms in an ocean beneath the cloud tops. Above the clouds, the sky is hydrogen. Beneath them, perhaps, a global ocean turns slowly, with whatever currents and tides and chemical disequilibria a planet of that size would produce. We do not yet know whether anything is alive in that ocean. We know the chemistry is right. We know the temperature is right. We know the atmosphere is the right combination for the Hycean model. The next several years should bring further answers. Until then, the planet can be held softly. A world we have looked at long enough to recognize, but not yet long enough to know. Part 9. The broader catalogue of named candidates. Beyond the headline systems, the broader catalogue of confirmed and candidate habitable zone worlds is now several dozen names long. None of these planets has yet been characterized in the detail that Kepler 22b, Proxima b, TRAPPIST 1e, or K2-18b have received. Most of them are known only by their basic transit parameters or radial velocity signatures. A few have had initial atmospheric reconnaissance. None has been confirmed inhabited. Each of them, however, contributes to the population picture, and each represents a real specific world somewhere in the catalogue, with its own particular history and its own particular set of chances. A walk through the broader catalogue is worth taking slowly. Each entry is a name on the list. Each name corresponds to a place. The script can let the catalogue spread out across this part as a slow inventory without trying to dramatize any single entry. The sheer length of the list is the gentle point. Gliese 581. G was one of the earliest claimed habitable zone candidates, announced in 2010 as a possible Earth mass planet in the habitable zone of an M dwarf at 20 light-years from Earth. The detection was later disputed, and the planet's status remains uncertain. Some statistical analyses suggest the signal is a stellar artifact rather than a planet. Others continue to support its existence. The Gliese 581 system contains several confirmed planets at various orbital distances, including a candidate, Gliese 581d, that may sit just outside the conservative habitable zone. The system as a whole has been one of the longest-running test cases for the limits of radial velocity detection around active M dwarfs. Gliese 832c, at 16 light-years, is a super-Earth of about 5 Earth masses in the habitable zone of an M dwarf host. It was confirmed in 2014 by combined radial velocity and transit timing analysis. It has an orbital period of about 36 Earth days. It is probably tidally locked. Its atmospheric status is unknown. Kepler 442b, at 1,190 light-years, is a confirmed habitable zone super-Earth of about 1.3 Earth radii around a K-type star. The planet was announced in 2015. Its host star is slightly cooler than the Sun, with a habitable zone that places the planet at about 240 days of orbital period. The planet has been highly ranked on Earth Similarity Index calculations, sitting around 0.83. It is one of the most Earth-similar of the Kepler catalogue planets around stars that are not M dwarfs. Kepler 438b, at 470 light-years, was announced in the same 2015 press conference. It is a confirmed habitable zone super-Earth of about 1.1 Earth radii around an M dwarf. Its orbital period is about 35 Earth days. Its host star is moderately active. Some analyses have suggested the planet may experience significant atmospheric stripping due to host star activity. Kepler 1130b, at 550 light-years, is a habitable zone planet of about 1.66 Earth radii around a Sun-like G-type star. It is one of the Kepler catalogue planets that sits comfortably in the habitable zone of a Sun analogue, similar in concept to Kepler 22b and Kepler 452b. Kepler 1174b, at 790 light-years, is a habitable zone super-Earth of about 1.5 Earth radii around a K-type star. It is another older cousin candidate. Its host star is about 7.5 billion years old, more than 3 billion years older than the Sun. Kepler 1283c, at 640 light-years, is a habitable zone planet of about 1.8 Earth radii around a K-type host. The planet is among the larger habitable zone candidates in the Kepler catalogue, sitting at the boundary between super-Earths and mini-Neptunes. Kepler 1410b, at about 1,600 light-years, is a confirmed habitable zone planet of about 1.8 Earth radii around an early M dwarf. Its orbital period is about 60 days. The list continues. Kepler 1638b, Kepler 460b, Kepler 1544b, Kepler 1649b, Kepler 1649c, Kepler 153.8b, Kepler 93.9c, and several dozen others. The Kepler catalogue alone contains around 50 named planets that meet at least the basic criteria for habitable zone candidacy. Most of them are around M dwarfs, with the standard M dwarf caveats. A smaller fraction are around K dwarfs or G dwarfs, where the host star is calmer and the prospects for atmospheric retention are better. Beyond Kepler, the TESS mission has begun to fill in the catalogue of nearby habitable zone candidates. TOI 700d, at 101 light-years, is a small habitable zone planet of about 1 Earth radius around an M dwarf. TOI 2285b, at 42 light-years, is a candidate habitable zone planet around a K-dwarf. TOI 1906b, TOI 2576b, and several others are now candidate habitable zone worlds around stars within a few hundred light-years of Earth. There is also the candidate around Barnard's star. Barnard's star, at 6 light-years from Earth, is the second closest stellar system to the Sun. It is an old, very quiet M dwarf, with extremely low flare activity, making it one of the most habitability-friendly M dwarfs in the immediate stellar neighborhood. A candidate planet, Barnard's star B, was announced in 2018 as a super-Earth in a long orbit at the very outer edge of Barnard's star's habitable zone. The detection was later disputed and is now considered uncertain. More recent observations have suggested an alternative, much smaller, hotter planet on a closer orbit. The Barnard star system remains one of the prime targets for future direct imaging campaigns, but the question of whether it hosts a habitable zone world is still open. The candidate around Lalande, 21185, is also worth mentioning. Lalande, 21185, is the fourth closest star to the Sun, at 8.3 light-years. It is another quiet M dwarf. A candidate planet, Lalande, 21185b, has been tentatively identified at the inner edge of its host star's habitable zone. The planet is small, perhaps about 3 Earth masses, and probably tidally locked. Beyond the named candidates, there is a much larger population of statistically expected, but not yet detected, habitable zone worlds. The Kepler statistics suggest that, within 50 light-years of Earth, there should be on the order of dozens of habitable zone rocky planets around M dwarfs and several around K dwarfs and G dwarfs. Most of them have not yet been detected because the detection methods favor shorter period transits and closer-in radial velocity signals. The next decade of TESS observations and the next decade of radial velocity refinements should bring most of these planets out of the statistical estimate and into the named catalogue. By the late 2030s, the catalogue of named habitable zone planets within 50 light-years of Earth is expected to contain several dozen entries, each one a real specific world with its own particular characteristics. The script can let the broader catalogue land softly. The headline names Kepler 22b, Proxima b, Trappist 1e, K2-18b are the most studied, but they are not the whole list. The list is much longer. Most of its entries are little known outside the catalogue. Each of them is a real place. Each of them is somewhere in the galaxy, tracing its own slow orbit around its own host star tonight, while we are here, holding the catalogue gently from the inside. Part 10. The population, estimate, and Eta Earth. The catalogue, as it stands, contains perhaps 50 or 60 named habitable zone candidates with at least basic characterization. That is the floor of what we directly know. To answer the question of how many habitable planets are really out there at the galactic and cosmic scale, the small biased sample has to be extrapolated to the much larger population that current instruments cannot see. The extrapolation is, in its modern form, organized around a single number called Eta Earth. Eta Earth, written with the Greek letter eta, is defined as the average number of Earth-sized planets in the habitable zone per Sun-like star. It is the central statistic of modern habitability research. The number is small. It is also surprisingly stable across the various studies that have tried to measure it. Different research teams have produced different specific values, but the modern best estimates cluster between roughly 0.3 and 0.8. The most cited current estimate, from a NASA Ames analysis published in 2021, based on the full Kepler dataset, places Eta Earth around 0.5 for Sun-like stars. That means, on average, roughly half of all Sun-like stars in the galaxy host at least one Earth-sized planet in their habitable zone. A conservative interpretation pushes the number down, perhaps as low as 0.1, meaning roughly 1 in 10 Sun-like stars hosts a habitable zone Earth analog. An optimistic interpretation pushes the number up as high as 0.8, meaning roughly 4 out of every 5 Sun-like stars hosts such a planet. The honest current range is the entire span between these limits. The number is still being refined. Multiplying Eta Earth by the number of Sun-like stars in the Milky Way gives the most commonly cited figure for habitable planets in the galaxy. The Milky Way contains roughly 400 billion stars. Of those, perhaps 10% are G-type Sun-like stars, with the strict Sun analog definition. A broader definition, including K-type, cooler but still Sun-like stars, and the quietest M-dwarfs, raises that fraction substantially. By the strict definition, the multiplication yields roughly 20 billion Earth-sized habitable zone planets in the Milky Way around Sun-like stars. By the broader definition, including the M-dwarf population, the number climbs into the hundreds of billions. The headline figure that has entered popular coverage is the one most often quoted. The Milky Way may contain on the order of 40 billion Earth-sized habitable zone planets around stars that are at least roughly Sun-like in character. That is the conservative midpoint of the current estimates. It is not a precise number. It is a working order of magnitude. The honest range is from perhaps 2 billion at the most pessimistic end, considering only the strictest Sun analog stars and the lowest plausible Eta Earth values, to perhaps 100 billion at the most optimistic end, considering all stars that could plausibly host habitable worlds and the highest plausible Eta Earth values. These are the numbers behind the headline. The galaxy almost certainly contains somewhere between 2 billion and 100 billion planets in the habitable zone of their host star, with sizes consistent with being rocky. That is the flaw. Adding the hycean class, the icy moons, the rogue worlds, and the broader, stretchier habitability definitions raises the number substantially. The full count of places in the Milky Way where life could plausibly exist may be much higher than the A-to-Earth figure suggests. It may be in the hundreds of billions or beyond. Extending from the galaxy to the universe, the observable universe contains, by current estimates, somewhere between 200 billion and 2 trillion galaxies. The lower end of the range corresponds to the latest deep field counts from JWST, which have revised the older estimates substantially downward. The Milky Way is a relatively large galaxy by population. Most galaxies in the universe are smaller, with fewer stars and fewer planets. The average per-galaxy habitable population is therefore probably somewhat lower than the Milky Way's figure. A reasonable rough estimate places the number of Earth-similar habitable zone worlds in the observable universe at somewhere between 10 to the 18th and 10 to the 22nd, between 1 quintillion and 10 sextillion. The script can let those numbers land without trying to make them feel comprehensible. They are no longer numbers in the felt sense. They are a way of saying that, by every reasonable extrapolation from current evidence, the universe contains an essentially uncountable population of habitable worlds. The Drake equation, the formal version of this multiplicative reasoning, organizes the same logic. The number of currently communicating civilizations in the galaxy is expressed as a product of 7 factors. The rate of star formation, the fraction of stars with planets, the average number of habitable planets per such star, the fraction of habitable planets on which life arises, the fraction of those on which intelligence arises, the fraction of those that develop communicative technology, the average lifetime of such civilizations. Most of these factors, until the past 2 decades, were almost entirely unknown. Some have now been bracketed. The rate of star formation in the galaxy is well measured. The fraction of stars with planets is now known to be essentially 1. The average number of habitable planets per such star, A-to-Earth, has been narrowed to between 0.1 and 0.8. The remaining factors, the abiogenesis probability, the intelligence probability, the technology probability, the civilizational lifetime, remain unknown by many orders of magnitude. The first half of the Drake equation has been substantially answered. The second half remains open. We now know how to count habitable worlds with reasonable precision at the population level. We do not yet know what fraction of them host life, what fraction of those host intelligence, what fraction of those develop technology, and how long such civilizations persist. The gap between the first half and the second half is the size of the unknown that the question still carries. The script can hold the Drake equation gently. It is not a calculation in the precise sense. It is a structure for organizing our ignorance. The known terms tell us that the galaxy is full of places where life could begin. The unknown terms leave open whether life actually does begin, and whether, having begun, it persists, and whether, having persisted, it ever becomes anything that could be detected from across interstellar distances. The honest current position is that the headline number, the count of habitable worlds, is robustly large. The downstream questions about what fraction of those worlds are inhabited, what fraction are intelligently inhabited, and what fraction are communicatively inhabited, are still entirely open. There is a small correction worth making before moving on. The phrase tens of billions, often used in popular coverage, sometimes carries the false implication of certainty. The galaxy has tens of billions of habitable planets. The honest statement is more conditional. If the conservative habitable zone definition is correct, and if the current best estimates of eta Earth are correct, and if the broader definitions of habitability are not added in, and if the various architectural constraints do not reduce the count further, then the Milky Way contains tens of billions of plausibly habitable worlds. Each one of those ifs is itself a source of uncertainty. The range is wide. The midpoint is the headline. The midpoint is also probably not the answer. The script should let this land softly. The population estimate is real. The galaxy almost certainly does contain very large numbers of habitable worlds, even by the conservative definitions. The exact number depends on factors that are not yet fully measured. The order of magnitude is settled. The precision is not. The next decade of observations, particularly from the upcoming Habitable Worlds Observatory and the Roman Space Telescope Microlensing Survey, should narrow the range considerably. By the early 2040s, the population estimate may be considerably tighter than it is now. Until then, the working answer to the question of how many habitable planets are really out there is something close to this. In our galaxy alone, somewhere between several billion and several hundred billion, depending on how generously habitability is defined and how the various uncertainties resolve. Across the observable universe, somewhere between 1 quintillion and 10 sextillion. The honest answer carries both ends of those ranges, gently, at the same time. The number is large. The exact value is not yet known. The order of magnitude is large enough that the question of whether the galaxy is full of habitable worlds is, at this point, essentially settled in the affirmative. The question of whether any of those worlds are inhabited is still wide open. Part 11. The conditional probabilities and the filter. The headline number, tens of billions of habitable zone worlds in our galaxy alone, is large enough that the question naturally moves from how many to which. Of all those plausible homes, how many actually host life? That second question, the conditional probability question, is the one that turns the headline number from an answer into the beginning of a different conversation. A habitable world is not the same as an inhabited world. The transition from the first to the second depends on a chain of conditional probabilities, each of which is, by current evidence, unknown. The first probability is biogenesis. Given a habitable planet, with the right architecture, and the right chemistry, and the right energy gradients, what fraction of such planets actually have life arise on them? Is biogenesis common, occurring readily under any reasonable conditions? Or is it rare, a fantastically improbable event that has happened only once on the one world we know about? We have one example. We do not know whether it is typical or anomalous. The second probability, conditional on the first, is the transition from simple to complex life. On Earth, life arose within perhaps a few 100 million years of the planet's formation, while it took roughly 2 billion more years for complex multicellular life to emerge. The transition from prokaryotic to eukaryotic cells appears, by every available indication, to have been an extraordinarily rare event. Possibly only one such transition has ever occurred in Earth's entire history. Whether eukaryotes are a universal feature of long-lived biospheres or a one-time accident is one of the deepest open questions in biology. The eukaryotic transition is one of the leading candidates for the bottleneck step that may explain the apparent rarity of complex life. The third probability, conditional on the second, is the transition from complex life to intelligence. On Earth, complex multicellular life has existed for roughly 600 million years. Recognizably intelligent animals, capable of tool use, social learning, and complex problem-solving, have existed for at most a few tens of millions of years. The current human-level intelligence, with language and symbolic thought, and the capacity for cumulative cultural learning, has existed for perhaps a few 100,000 years. The transition is recent. It may be one time. It may be inevitable, given enough time. We do not yet know. The fourth probability, conditional on the third, is the development of communicative technology. On Earth, technologically capable civilization has existed for at most a few thousand years, and radio-emitting civilization for about 1 century. The window in which a civilization is capable of being detected across interstellar distances is short, at least so far. Whether technological civilizations typically persist for thousands of years, millions of years, or only decades is unknown. The window's length is the variable that most directly affects whether we should expect to see other civilizations now. These 4 conditional probabilities, multiplied together, determine what fraction of habitable worlds host detectable communicating civilizations. The product is unknown by many orders of magnitude. The best available estimates span from 1 in 1 billion to nearly 1 in 1. There are scientifically respectable positions at both extremes. The Copernican position, that life and intelligence are common, treats the conditional probabilities as relatively large and predicts that the galaxy should contain many detectable civilizations. The rare Earth position, that the chain of probabilities is extraordinarily narrow, treats the product as small enough that Earth may be one of very few inhabited worlds in the galaxy, or perhaps the only one. Both positions are consistent with current evidence. The rare Earth hypothesis is worth a small additional pause. The argument is that the architectural conditions for long-lived complex life are narrower than the simple habitable zone definition implies. The argument lists, among other requirements, a host star of the right type, neither too small nor too large nor too active, a galactic location in the habitable annulus, away from frequent supernovae and gamma-ray bursts, a protective gas giant architecture with large outer planets shepherding debris away from the inner system, a planet of the right size, in the right orbit, with the right composition, with a strong magnetic field, with plate tectonics, with a large stabilizing moon, with a long-lived atmosphere, with persistent oceans, with a stable rotational axis, with a low rate of impacts, with a stable orbital configuration, with sufficient time, with all of these conditions met simultaneously and persistently for billions of years. Each individual condition is plausible. The conjunction of all of them may be very rare. The counter-argument is that we do not have a representative sample. We have one example of a habitable planet, and on that one example, life arose, complexity emerged, intelligence developed, and technology followed. The single example tells us that the conditional probabilities are not zero. It does not tell us how small they are. The Copernican position holds that we should expect Earth to be roughly typical of habitable worlds, not extraordinarily rare among them. The fact that life arose here within a few 100 million years of the planet becoming habitable suggests that biogenesis may not be as bottlenecked as the rare Earth hypothesis implies. The frequency of Earth-similar habitable worlds, as estimated by Eta Earth, is high enough that even modest values for the conditional probabilities would yield millions or billions of inhabited worlds across the galaxy. The honest current position is that both views are scientifically respectable. The available evidence does not decisively favor one over the other. The script should hold the gap honestly. We do not yet know whether the galaxy is full of life or whether Earth is the only world where it has emerged. The next decades of biosignature observations, particularly from the Habitable Worlds Observatory, should begin to narrow the range. If even one nearby habitable world is found to have an atmosphere with clear biosignatures, the rare Earth position becomes much harder to sustain. If the first dozens of nearby habitable worlds all turn out to be lifeless, the rare Earth position becomes much more plausible. A related framing, often discussed alongside the rare Earth hypothesis, is the Great Filter. The idea is that somewhere along the chain from a habitable world to a communicating civilization, there is at least one filter, at least one step that is fantastically improbable, sufficient to explain why we do not see other civilizations in the galaxy, despite the high frequency of habitable worlds. The filter could be behind us. If the rise of complex life is the filter, or if the transition to intelligence is the filter, then we have already passed through the narrow gate, and the rest of the chain may be relatively easy. The filter could be ahead of us. If the long-term survival of technological civilizations is the filter, then we may not yet have reached the bottleneck. We may be approaching it. Whether the filter is behind or ahead is not currently known. The honest answer is that we do not have enough information to distinguish. The arguments for a behind-us filter rest on the apparent rarity of certain biological transitions in Earth's history. The arguments for an ahead-of-us filter rest on the difficulty of long-term planetary survival in the face of self-generated existential risks. Both are coherent. Both are testable, in principle, by future observations. The script does not need to dwell on great filter speculation. The video is about habitable worlds, not about Fermi paradox philosophy, but a brief, calm acknowledgement that the gap between habitable and inhabited is one of the deepest open questions in modern science is appropriate. The headline number, tens of billions of plausibly habitable worlds in the galaxy, becomes much smaller when each habitable world is multiplied by an unknown conditional probability of being inhabited. The inhabited population may be in the billions. It may be in the millions. It may be in the dozens. It may be one. We do not yet know. There is also the third factor that the conditional probability chain has to be held alongside, which is the silence itself. Several decades of radio searches, several decades of optical laser searches, and several decades of waste heat infrared surveys have produced no confirmed evidence of any technological civilization anywhere in the galaxy. The silence is real. It carries information. The script should hold it gently. It may mean we are alone. It may mean we are too early, with most civilizations still in the future. It may mean civilizations are quiet by design, deliberately not broadcasting. It may mean we are not yet listening correctly, with our instruments tuned to the wrong frequencies or our searches confined to the wrong parts of the sky. The silence is consistent with all of these explanations. It does not yet distinguish between them. The honest landing place for this part is the gap itself. The galaxy contains many places where life could exist. We do not yet know whether life is in any of them. The catalogue of habitable worlds is real. The catalogue of inhabited worlds beyond Earth is currently empty. The gap between the two catalogues is the size of the conditional probabilities, multiplied by the silence, divided by whatever fraction of that signal we are currently capable of detecting. The number that emerges from the multiplication is one of the most important unknowns in modern science. The next several decades may begin to close in on it. Until then, the catalogue's headline number remains true, and the catalogue's inhabited number remains, for now, 1. Part 12. What the next 2 decades will show. The question of how many habitable worlds are out there is, in one important sense, no longer entirely open? The answer is large. The galaxy contains plausible, habitable worlds in the billions or tens of billions, and the universe contains them in quantities that no longer translate into the felt sense of number. The remaining question of how many are inhabited is the question that the next 2 decades of observation are designed to begin to answer. The first instrument shaping that horizon is the James Webb Space Telescope. JWST has been operating since the middle of 2022 and has now produced atmospheric characterizations of several of the most observationally accessible habitable zone candidates. The TRAPPIST-1 observations, with their initial findings of no thick atmospheres on the inner 2 planets, have softened expectations for ultra-cool dwarf habitability. The K2-18b observations, with their detection of methane and carbon dioxide and the contested signal of dimethyl sulfide, have raised expectations for hycean habitability. The next several years of JWST observations will refine both of these pictures considerably and will add atmospheric data on additional candidates. By the late 2020s, the field's expectations for which kinds of worlds retain atmospheres and which kinds host the chemical signatures of biological activity will be much more sharply defined than they are now. The second instrument is the Roman Space Telescope, scheduled to launch in the late 2020s. Roman will conduct a wide-area microlensing survey expected to discover thousands of new exoplanets, including large numbers of cold, distant, or free-floating worlds that current instruments cannot detect. The population statistics for habitable worlds, particularly the long-period worlds that the transit method cannot easily reach, will sharpen significantly once Roman is operational. The eta Earth value, currently bracketed between 0.1 and 0.8, may be narrowed to a much smaller range. The free-floating rogue planet population, currently estimated only roughly from existing microlensing data, will be characterized in much greater detail. The number of cold subsurface ocean worlds in the galaxy may, by the early 2030s, be an observationally constrained number rather than a statistical estimate. The third instrument, or rather the third class of instruments, is the trio of extremely large ground-based telescopes currently under construction. The Extremely Large Telescope in Chile, with a 39-meter primary mirror. The Giant Magellan Telescope, also in Chile, with 7 8.4-meter primary mirrors arranged in a single optical system. The 30-meter telescope, with a 30-meter primary mirror in Hawaii. All 3 are expected to begin scientific operations in the late 2020s or early 2030s. Each will be capable of measuring the atmospheric composition of planets around the nearest stars by direct imaging and high-resolution spectroscopy. If Alpha Centauri A or B hosts an Earth analog planet, these telescopes will likely detect it. If Proxima B has a thin remnant atmosphere, they should be able to characterize it. If any of the nearest dozens of habitable zone candidates have biosignatures in their atmospheres, the extremely large telescopes will have a strong chance of finding them. The fourth instrument is the one specifically designed to answer the question of biosignatures on Earth analog worlds. The Habitable Worlds Observatory is a NASA flagship mission currently in concept development, with a projected launch in the early to middle 2040s. Its specific design goal is to image at least 25 Earth analog planets around Sun-like stars and obtain spectroscopic atmospheric characterizations of each. The mission is the direct successor to the Hubble and James Webb Space Telescopes in the flagship lineage. Its central scientific objective is the search for biosignatures on Earth analog worlds around nearby Sun-like stars. If the mission flies on schedule and meets its design specifications, The question of whether any of the nearest 25 Sun-like stars hosts a planet with the chemical signatures of life will be substantially answered within roughly 20 years from now. That is the timeline. The question of whether the galaxy is full of inhabited worlds will likely begin to be answered, at least at the small sample level, within the next 20 to 30 years. The answer may be yes. It may be no. It may be ambiguous, with some candidates showing tentative biosignatures and others showing clear signals of lifelessness. In any of those cases, the field's understanding of how the headline number of habitable worlds translates into the deeper number of inhabited worlds will be substantially refined. There are smaller instruments contributing as well. The Plato mission, scheduled to launch in the late 2020s from the European Space Agency, will conduct long-duration transit surveys of bright Sun-like stars to search for Earth-analog planets with orbital periods of months to years. The Ariel mission, also from ESA, will conduct atmospheric characterization of hundreds of exoplanets in the warm-to-hot range. The ground-based extreme precision radial velocity programs, including Espresso at the Very Large Telescope, Maroon X at the Gemini North Telescope, and Express at the Lowell Discovery Telescope, are pushing radial velocity precision into the range where Earth-mass planets around Sun-like stars can be detected. Each of these contributes its own piece to the picture. There is also the longer horizon class of instruments, in early planning or early concept stages, that may begin to operate in the 2050s or beyond. The LUVOIR concept, which preceded the Habitable Worlds Observatory in mission planning. The Ptolemy Small Telescope mission, designed specifically to monitor Alpha Centauri A and B for Earth-analog planets through astrometric astrometry. Various proposed direct imaging space-based interferometers capable in principle of resolving surface features on the nearest Earth-analog planets. Various proposed deep space telescopes positioned at the Sun's gravitational lens focal point, capable in principle of imaging surface features on exoplanets at extremely high resolution. None of these are funded missions. All of them represent the trajectory of what may become possible in the second half of the 21st century. The script can hold them gently. They are the long horizon. The shorter horizon, the JWST through HWO arc, is the one most relevant to the question we are sitting with tonight. There is also the question, often raised in popular coverage, of whether direct probes to nearby habitable zone candidates are possible. The honest answer is that with current technology, no. The nearest candidate, Proxima b, is 4.24 light-years away. The fastest spacecraft ever launched, the Parker Solar Probe, has a peak speed of about 150 kilometers per second. At that speed, the journey to Proxima b would take about 8,500 years. Proposed propulsion concepts, including light sails accelerated by laser arrays, beamed energy propulsion, fusion drives, and antimatter drives, could in principle reduce the journey time to decades, or perhaps centuries. None of these technologies currently exists at the engineering level required. The Breakthrough Starshot Initiative, which has been working on the light sail concept for the past several years, has a tentative goal of launching a small fleet of gram-scale probes toward the Alpha Centauri system on a roughly 20-year journey. The timeline for the first launch, if it happens, is currently mid-century or later. Even in the most optimistic scenario, the first close-up data from any nearby habitable zone candidate would arrive in the second half of the 21st century, or the early 22nd. For the foreseeable future, the question of habitable world habitability will be answered by remote observation, not by direct probe. The atmospheres, surfaces, and possibly biosignatures of these worlds will be read out by the instruments listed above. The answer to whether any of them host life will come from spectroscopy across light years, rather than from instruments at the worlds themselves. The script can hold this softly. The answers we are waiting for are coming. They are coming relatively slowly. They will arrive piece by piece, candidate by candidate, biosignature by biosignature. The first confirmed biosignature on any exoplanet, if it comes, will be a turning point comparable to the first confirmation of an exoplanet itself in the mid-1990s. Whether that confirmation arrives in 2030, 2040, 2050, or never, is the question that the next several decades will answer. In the meantime, the catalogue grows. New candidates are added every month. The named worlds we have walked through: Kepler 22b, Kepler 452b, Proxima b, the TRAPPIST, 1 planets, K2-18b, the broader Kepler and TESS catalogue, all continue to be observed. New atmospheric characterizations are reported. Old detections are refined or revised. The catalogue is, in a quiet way, one of the most actively maintained inventories in modern science. The script can let the next 2 decades land softly. They will bring answers we do not yet have. They will not bring all of them. The full answer may be a generational project. It is one of the larger questions any generation has tried to ask. It is also a question that has, for the first time in human history, the right instruments pointed at it. Part 13, the closing reframe. The honest answer to the question of how many habitable planets are really out there is, in the end, a layered one. We know with certainty of exactly one inhabited world. That world is Earth. It is the calibration point. It is the place where the question is being asked from. It is the one example we have, and it remains, by every direct measurement, the only known case. We have plausible candidates in the dozens. The named entries in the catalogue: Kepler 22b at 620 light-years, perhaps an ocean world, perhaps a gas-shrouded mini-Neptune, the first habitable zone planet ever confirmed around a sun-like star. Kepler 452b at 1,400 light-years, perhaps a slightly older cousin to Earth, perhaps a runaway greenhouse failure already underway. Proxima Centauri b at 4.24 light-years, the nearest known potentially habitable world, perhaps a thin atmospheric terminator twilight planet, perhaps a stripped airless surface. The TRAPPIST-1 system at 39.6 light-years, 7 Earth-sized rocky worlds around a star that will burn for trillions of years. K2-18b at 124 light-years, the first candidate hycean world with atmospheric signatures of methane and carbon dioxide, and the tentative whisper of dimethyl sulfide. Kepler 1649c, Kepler 186f, the broader Kepler and TESS catalogue of named candidates. Each one a real specific world. Each one with its own particular chances. Each one currently being observed or waiting to be observed by the next generation of instruments. We have statistical estimates suggesting that the galaxy contains somewhere between several billion and several hundred billion plausibly habitable, Earth-similar worlds. We have estimates suggesting that the observable universe contains somewhere between 1 quintillion and 10 sextillion. The numbers are large enough that the order of magnitude no longer translates into a felt sense of size. The galaxy is full of plausible places. The universe is fuller still. What we do not know is the most important thing. We do not know how many of those worlds are actually inhabited. We do not know what the silence we hear in our radio telescopes is telling us. We do not know whether biogenesis is common or vanishingly rare. We do not know whether the conditional probabilities chain from habitable to inhabited, to intelligent to communicative, is high enough at each step to populate the galaxy with many other civilizations, or low enough at some single step to keep the galaxy almost empty. We do not know whether the long quiet of the universe is a quiet of emptiness or a quiet of distance and timing. The headline figure that some scientists, in informal moments, have put as high as 99%, the framing that the odds of life on planets like Kepler 22b are effectively certain, expresses something real. The discovery of habitable zone worlds around sun-like stars, so soon after the search began, was not the conservative prediction. The frequency of such worlds turned out to be much higher than expected. The chemistry of life turned out to be embedded in the chemistry of the universe itself. The first hints of biosignatures on a hycean candidate 124 light-years away are now being read out of the atmosphere. None of that is small. None of it is to be dismissed. The figure also, however, is to be held gently. It is an expression of enthusiasm, not a formal probability. The actual conditional probabilities remain unknown. The silence remains real. The catalogue of confirmed inhabited worlds remains, for now, 1. The next several decades of observations may close some of that gap. They may also leave it open. The question itself is large enough that even partial answers will be major achievements. A small reframe before we close. The number that matters, in the most direct sense, is not the number of habitable worlds. It is the number of inhabited ones. The two are connected but distinct. A galaxy with tens of billions of habitable worlds and one inhabited world is, in a real sense, almost as quiet as a galaxy with one habitable world and one inhabited world. The headline number can be enormous, and the felt experience of cosmic loneliness can still be exactly what it is here, tonight, on a small, wet, rocky planet in a quiet G-type system, halfway out along a spiral arm of one ordinary galaxy. The headline number does not, by itself, populate the sky with company. Whether the company is there or not is a separate question, and one we cannot yet answer. A second reframe. Even if the inhabited count is small, the habitable count remains real. Tens of billions of worlds, in our galaxy alone, with temperatures and atmospheres and oceans in which life as we know it could plausibly exist. Each one, by itself, a place that the universe has prepared for the possibility of life, whether or not life ever takes the offer. The preparation, on its own, is something. The universe has been making rocky planets in the right temperature ranges, around the right stars, in the right galactic locations, for billions of years. Most of those preparations never see anything happen. The chemistry sits ready and unused. The oceans turn beneath atmospheres that never produce anything to swim in them. The terminator rings of tidally locked planets stay in permanent twilight without anyone to walk under their dim red dawns. The preparations are still real even when they go unused. A third reframe. The question of how many habitable planets are really out there is also, in a quieter sense, a question about what habitability itself means. The conservative definition, surface water at 1 bar atmospheric pressure, is one answer. The optimistic definition, the broader range that admits past Venus and past Mars, is another. The hycean definition, which adds sub-Neptune ocean worlds, is a third. The subsurface ocean definition, which adds icy moons and rogue planets, is a fourth. Each definition produces a different count. Each one is a different statement about what we are looking for. The headline number depends on which question is being asked. The answer is large by every available definition. The closing reframe is this. The question, how many habitable planets are really out there, has, by the best current evidence, the same kind of answer regardless of which version of the question we ask. The answer is large. The galaxy contains tens of billions, or perhaps hundreds of billions, of plausibly habitable worlds. The universe contains them in numbers that no longer translate into felt size. Whether any of them are inhabited remains open. The first confirmation of an extraterrestrial biosignature, if it comes, will probably arrive in the next 20 to 30 years. The first direct observation of an inhabited world will probably arrive later still. The first communication with another intelligence, if it ever happens, is on a timescale we cannot yet estimate. In the meantime, we have the catalogue. The catalogue is real. Each entry in it is a real place. Somewhere in the Cygnus constellation tonight, a possibly oceanic world is tracing its 290-day orbit around a star slightly cooler than ours. Somewhere in the Centaurus constellation tonight, a small rocky world is locked into permanent day and night around the dim red dwarf nearest to us. Somewhere in Aquarius tonight, 7 Earth-sized worlds are resonating around an ultra-cool dwarf that will burn for trillions of years. Somewhere in Leo tonight, a hydrogen-skied ocean planet is turning slowly with the faint chemistry of methane and carbon dioxide, and perhaps the soft whisper of organic compounds we cannot yet confirm. Each of those places is real. None of them will be visited in our lifetime. Most of them will never be visited at all. All of them are there. And so the answer that the question asks for, at its softest and most honest, is this. There are many habitable planets out there. The galaxy is full of plausible homes. The universe is fuller still. Most of them are dark. Most of them are silent. Most of them will never tell us whether anything is alive in them. A few of them, in the next several decades, may begin to answer. Until then, the question lives where it lives, somewhere between a single confirmed world and tens of billions of plausible ones, between the silence we hear tonight and the answers we may have within 30 years. The galaxy is large enough that the answer is almost certainly not zero. It is patient enough to keep its other lit windows hidden a while longer. Let your breathing slow. Let the night soften around you. Sleep well and good night.